Black holes can swallow anything, even light, and small black holes made from light itself may offer us abundant clean energy and a pathway to the stars. Black holes are enormously massive and dense objects, both in the wake of dying stars many times more massive than our own. But that may not be the only way to create them. One option proposed is to create Kugelblitz black holes, and while this originally referred to the suggested process for making them, it has also come to mean a class of micro black holes smaller than an atomic nucleus that could be used for powering spaceships or even civilizations. While there are many ways a black hole might be used for power or generation, these very small ones offer the easiest and most portable version, Hawking radiation. Today we'll be looking at the Kugelblitz black hole generation method, some variants on it, how that would function, how Hawking radiation works, what the scale of power generation and mass and lifetime would be for these black holes, and many potential applications, advantages, and limitations. If that sounds like fun, grab a drink and a snack before a black hole snatches it from you, relax, and please hit those like and subscribe buttons. Now, Kugelblitz is the German word for ball lightning, and it is a pretty good pick for the concept. As everyone knows, black holes are intensely massive objects, and mass generates gravity. But in reality, mass is just one type of energy, and other types of energy generate gravity. An object that is incredibly hot has actually increased its gravitational pull over that same object if it were cold, and so too, an object spinning very quickly has a lot of rotational energy and that adds gravity. Indeed, most black holes have as much as 20% of their energy in rotational format. They are also incredibly hot, but even photons generate gravity. Photons, the particles of light emitted by stars, and which cannot escape from a black hole's event horizon, can be added to a black hole, and their energy would add to its apparent total mass. In this same way, if we could manage to get a whole bunch of photons in the same time and place, at a high enough density, we could have enough energy there to generate an event horizon big enough to encompass them, and there is no known bottom limit for a black hole, though we'll discuss some possible limits later. For any given amount of mass or energy, there is a density it can be that if you crammed it down would form a black hole. The radius of black hole event horizon rises linearly with its mass or energy, but volume rises with the cube of radius, so that required density ends up inversely proportional to the mass. Something 10 times more massive only needs to be at 1/100th of the density to form a black hole. Something 1,000,000 times more massive only needs 1/1,000,000th of the density. As a result, you can make a black hole just by piling a lot of matter together that won't fuse, but we're still talking masses larger than our sun, even if we were piling up iron in one big ball. Even the big monster at the core of the galaxy, composed of several million suns worth of matter, is still denser than steel by a couple orders of magnitude, though there are some black holes that are less dense than thin air in the universe at large. Trying to make one this way would seem a bad approach, especially since we can move a naturally occurring black hole. They are actually amazingly efficient spaceship drives, though so massive it wouldn't generally be worth moving in favor of moving to. So instead we contemplate trying to make one much smaller than a star, and that's where we get into problems. Normally, a supernova occurs in the upper core of a star, blowing most of the matter there into space and imploding all the inner core, now made of iron, into a very tiny ball, so dense that it can't even be iron anymore, or any atom, but instead has to be degenerate matter. Indeed, it has to be a little denser than even a neutron star, which is around 10 trillion times denser than steel. Normal matter doesn't like being shoved together that tight, by which I mean fermions, which is the class of particles that includes protons, neutrons, electrons, and everything made from them, and are also named after physicist Enrico Fermi, from where we get the term Fermi paradox. Lots of things are fermions, and indeed it even includes neutrinos, and they barely interact with anything. Untold numbers of neutrinos hit Earth every instant. In fact, about 100 trillion hit you every second, and yet only a handful would actually interact with any atoms while passing through you or this planet. In the super-dense hearts of dying stars is one of the few places things are dense enough that they tend to get absorbed, which is how we get many heavy elements. Stick enough neutrinos in one place and you've got a black hole. Same for something else weakly interacting like dark matter, which may or may not be a fermion itself. Neither is very easy to handle though, so we imagine a different option: bosons. Bosons are a different category of particle and include photons of light, gluons, Higgs bosons, and even some particles made of pairs of quarks, instead of the 3 quarks protons and neutrons are made from. What's particularly interesting about bosons is they don't mind being in the same place as each other. You can stack them up. Indeed, when we talk about wavelength of light, you can't think of that as the actual size of a photon of light, and counterintuitively, the more energy a photon has, the smaller its wavelength. So gamma rays are basically on an order of atomic nuclei, while X-rays are more at the atomic, and visible light we can see, plus its neighbors in ultraviolet and infrared, as more on the size of molecules and cells. Alternatively, a microwave photon is on the human scale, and longer radio frequencies can even be as big as a planet, while perversely holding virtually no energy. And even a normal gamma-ray photon might hold 1 billion trillion times as much energy in something as small as an atomic nucleus. Indeed, if we could arbitrarily generate a photon of whatever energy we wanted, you could have one so short in wavelength and high in energy it would meet the qualifications to have an event horizon, and that is the notion that gets played with in some quantum gravity and cosmology discussion. We talked about that more in our episode Things Which Will Never Exist, and generating such a particle isn't something we have an apparent avenue to, so we'll leave that there for today. But these bosons, whatever their energy and wavelength, can all be in the same place at once, intersect freely, and keep on moving. Even with bosons, there are some issues with packing them too tight, which we'll get to in a moment. If we imagine some perfect sphere of a mirror that let light of a certain wavelength in but not back out, just like a black hole does, then we could pump that thing with energy until its energy density tipped over the threshold to be a black hole. If we imagine we did that with a sphere half a micron across, able to absorb blue light, which has a wavelength of about half a micron, then all we would need to do is stuff in a lot of photons. 15 trillion joules of energy worth, in fact, which is roughly 1200 years of power production of our entire sun. That would seem a little hard to pull off, but something like X-rays at 1,000 times the energy and 1,000th the wavelength of a blue photon, or even more, could cram into a smaller spot and need only 1,000th the energy to do it. So basically 1 year of solar production. Channel regulars have probably heard me mention before that even civilizations that are interested in growing their population into the quadrillions might still build a Dyson swarm for technologies like this, and we'll come back to why that might be the case in a bit. But since we do not have any 100% perfect one-way mirrors, the idea is to try to time a lot of laser blasts to arrive at the same place and time very accurately, so that for that briefest moment they are a big ball of energy, hence the Kugelblitz or ball lightning name. To give some scale here, since light moves 300 million meters per second, and in our blue light case we are contemplating something half a millionth of a meter wide, the time a given photon would be passing through there is only a femtosecond, a millionth of a billionth of a second, and the X-ray has to do even better, hitting a spot the size of an atom that it passes through in a billionth of a second, or an attosecond. Needless to say, that's quite a small window to be trying to dump the entire annual output of the sun into, and you presumably have to have mirror arrays able to bounce a beam of light around without major dissipation for a full light year to get the entire annual solar output in one spot at one instant. It's a lot of energy too, but to think of it in terms of mass, that blue Kugelblitz black hole has a mass equivalent to a fifth of Ceres, the largest asteroid, and the one so big we debate if it should be called a dwarf planet instead. While the mass energy of our X-ray example would be on an order of 200 Mount Everest crammed into something the size of an atom. They are also way too big to be of use to us for Hawking radiation, as Big Blue isn't even quite generating a single joule of energy in a whole year. It might be big enough for a post-biological and post-stellar civilization though. See our episode Black Hole Farming for details, though we'll cover it a bit today too. The Atom X black hole could at least run an LED light bulb we could see in a dark room. Not a lot of power, but more importantly, it is generating that power consistently for 7 billion years, and Big Blue even longer. only it isn't consistent. As it gives off power, it loses mass and generates more power. Any black hole, given a long enough time period, will generate useful amounts of energy. Just don't hold your breath. Most wouldn't do so for so long a time that they'd view the entire history of our universe, from the Big Bang to the last star, as less than a blink of an eye in a very long life. We would love to create smaller black holes, but you really can't do one smaller than you could generate a beam for, or make a material you can reflect, since materials are made of multiple atoms and gamma rays are smaller than atoms. They don't reflect well. As of the time of this writing, the smallest wavelength laser I'm aware of is 0.15 nanometers, just a little smaller than our X-ray example, with a power output of 35 milliwatts and working out to a mass of almost exactly 10 to the 17 kilograms or 100 trillion megatons. We'll be using megatons and kilotons a lot in our discussion going forward, but the key thing here is that we can't really make this and use it for useful Hawking radiation, not unless we want to wait a billion years. However, it is a lot bigger than an atomic nucleus, so we could start feeding it matter and faster than it was oozing power out. Mind you, you have to add the equivalent of 250 million neutrons or protons to this thing every second to add mass faster than it is losing, but that should be possible given that a line of nucleons flying at near light speed can still be spaced nearly a meter apart coming out of their cannon, and you could have multiple beams on it and add more and speed it up as it grew. Though with the caveat that even if you were feeding this at several hundred times its minimum feed rate, you might need longer than the universe has been around to get something big enough to feed matter in as fast as you could want. But you could also just keep whatever beam you used to make it on until it got big enough to force feed normal matter. So I would bump this into the category of scientifically solid and engineering feasible. And it is why we spent a lot of time talking about micro black holes on this channel, and indeed did a whole episode on black hole technologies last month that was not focused on Hawking radiation black holes. Because a big but tiny black hole the size of an atom can still generate power by other methods, as can anything bigger than that and much easier too. Time will tell if we can make and manipulate higher energy beams to make even smaller black holes. Now, what's all this black hole Hawking radiation stuff? In the aforementioned episode, I did cover the virtual particle explanation in some detail, though we'll go over it briefly today, and we'll also give a non-virtual particle explanation. The very confusing thing about Hawking radiation for most folks is that smaller black holes give off much higher amounts of radiation. As mentioned, we did the virtual particle explanation in last month's episode on black hole technologies, and the two-paragraph summary of that is that the quantum foam everywhere in this universe is constantly spawning huge quantities of virtual particles in pairs that self-annihilate. The rate at which this happens is the same everywhere, near a big black hole or a small one, or inside your finger or thumb, and the energies involved are staggering and mind-boggling. Sometimes the place they emerge, though, is where an incredible amount of force is at play, and one that varies heavily in strength even over subatomic distances. This can rip those two virtual particles apart so they can interact with other particles or objects instead of annihilating. This doesn't happen simply by being near a big force field. Earth has a big gravity field, but the difference in strength from 1 kilometer to another is pretty minor, let alone from 1 nanometer to another. It is the sharp change in force that matters, and so even big black holes don't cause this effect much. Only very small black holes, and the smaller the better. It can happen with other forces incidentally, such as subatomic ones acting inside existing nuclei. See our antimatter factories episode or vacuum energy episode for further discussion. These virtual particles have a total of 0 energy in the pair, so one contains negative energy, and over time, the black hole absorbs more of the negative energy particles and loses mass, while emitting those positive energy photons into the wider universe. That's the virtual particle explanation, and they are more of a calculation device than a real object, though the word real is pretty ambiguous in cosmology and particle physics these days. It is not correct, and when folks think on it, they start wondering why the quantum foam, which constantly pops out brief-lived pairs of all sorts of particles, seems to be producing just photons for Hawking radiation, and why negative energy photons are the ones falling in. There is no reason that either should be true, but Hawking used it as his original popular explanation for Hawking radiation, so it gets reused a lot. This irritates a lot of physicists, but I happen to agree with Hawking that this is a simpler to explain and true enough version, which is why I often use it. But this is a construct for explanation. Much as it's energy, not just mass, that is warping spacetime, it is that actual warped spacetime that's emitting Hawking radiation. The greater and more severe that warping, the more energy can spill out of it. So in reality, it is not the event horizon emitting the radiation, it's the whole sharply curved area. It just sharpens the closer you get to the horizon, and beyond there too, but nothing is emerging from inside that horizon. As this energy emerges from that warped spacetime region several times larger than the event horizon, the overall warping decreases, resulting in the mass or energy of that black hole decreasing. If you want another version, then you may think of that region very close to a black hole as being very hot. Think of how a metal ball heats up as you bend it back and forth, and imagine that for spacetime itself in that spot, it is tortuously bent. This is how objects give off thermal light. In this case, that spacetime itself is so bent and hot that it does. And again, it's only the region safely out past the event horizon that we can see the light from, and it gets sharper and hotter as we approach. If none of those worked as a good mental analogy, then I'll simply say that the math demands that the region right near a black hole emits radiation, and that the sharpness of that curving matters way more than the size of the space being curved for how much radiation is emitted. So yes, a neutron star would also emit Hawking radiation, and so would a white dwarf, or even you or I. But given that even a neutron star bends space less than a normal black hole, and a normal stellar mass black hole's bending near its event horizon is still so small, it takes a trillion years to leak most of its radiation out, we can discard these all as meaningful producers of Hawking radiation. It also does mean that we could at least consider that since it really warped space-time producing its effect, which you might think of as cracks in space-time letting vacuum energy leak out, that we could do this without mass or even energy, if we had some way to sharply bend space-time without either. And the Kugelblitz approach is about doing it without mass, but with energy, and we want to think of it as slicing a hole through the universe with a very powerful laser into the true vacuum, or pushing down on a rubber sheet with it so that it slowly relaxes back to where it was, gradually emitting the energy you bent that sheet with. Those analogies seem as right as the virtual particle analogy Hawking offers. I would be curious which, if any, you found most clear for the concept though, since I must explain the idea a lot, and without much math. So, how tiny and compressed does space-time need to get to give us useful Hawking radiation? Well, that's obviously a bit subjective. In a cold post-stellar universe running on Landauer limit calculation, a whole civilization might thrive on a single watt of energy. See our Civilizations at the End of Time series for further discussion. And we might find a 1-watt black hole useful for something like a navigation beacon, or to power a low-energy device for 10 trillion years, about 1 trillion times longer than we expect before the stars all stop forming and die off. That would mass 18.9 million megatons, and I would put this as the extreme edge of what anyone would bother making unless they were planning to live off natural black holes when they evaporated, and they made a bunch of these to stagger their lifetimes as a bridge to that period. This is also probably more than enough to run a human-level emulation of a mind inside a virtual reality, offering them a lifetime of at least 10,000 trillion years, since they could certainly trickle-feed particles in from a greater stockpile to keep it running, as it is nearly atom-sized. Beneath this, every Kugelblitz is subatomic or smaller. To go through scales of power briefly, by hundreds, a 100-watt black hole masses 1.89 million megatons, and runs for 10 billion trillion years. A 10,000 watt or 10 kilowatt black hole masses 189,000 megatons, and would live for 10 billion years, and could easily run a fairly lavish household that whole time. A megawatt black hole masses 18,900 megatons, and could run a small community for 10 quadrillion years. A 100 megawatt black hole would be 1890 megatons and could replace most modern power plants for 10 trillion years, the period of time we think stars will exist in this universe, while a 10 gigawatt black hole at 189 megatons could match the output of our biggest hydroelectric power plants and do it for 10 billion years, the lifetime of our sun. At this range, we are getting black holes that could run real space habitats, and you may have noticed that while the power output has been rising by a factor of 100 each step, the mass has been dropping by a factor of 10, and the lifetime by a factor of 1,000. That's because at each step you've got an object a tenth as big generating 100 times the power, and thus burning out 10 times 100 or 1,000 times faster. At each step, our mass drops by a factor of 10, and so has the width of that black hole too, although there's nothing black about these, as even our 1 watt example would be able to dimly light a room, albeit with soft X-rays, not visible light, and only gets worse from there as we get into hard X-rays and then gamma rays. We can convert those X-rays into visible light, and same for gamma, much as we do in nuclear power plants. If you're curious, you could have a black hole that emitted a light spectrum similar to a normal star. It's just that it would be at about the 1 microwatt range, so not very useful for lighting things, as 20 billion megatons is not exactly portable. Back to our powers of 10 wattage scale, our next step would be a trillion watts, or a terawatt, at 18.9 megatons, and this would comfortably run even a full-scale Island 3 O'Neill cylinder complete with auxiliary facilities, and would do it for 10 million years. I think your sweet spot for artificial habitats and space stations is probably between here and our last step, the 10 billion year 10 gigawatt level. Note that you can use anything in between, or alternatively, just find your desired battery life and add several of that size instead till you reach your power requirement. That's not optimal for a spaceship though, and it's our next sizes that are in the top and bottom mass and power ranges for a spaceship. At 1.89 megatons, we have a black hole able to produce 100 trillion watts of power, and do so for 10,000 years. This is long enough to cross a decent chunk of a galaxy, but would not be enough for a trip across the entire galaxy or to a neighboring galaxy, where the 10 million year duration terawatt black hole might be needed instead. Of course, you could feed a smaller one to keep it alive, but that is just as precise as making one, and you're trying to stuff particles of fuel into a black hole just 5 billionths of a nanometer wide at this point, which is simultaneously emitting as much energy as the sun shines down on the whole state of Texas at noon. I'm not sure how you could get anything in there that was a normal bit of matter, and you might be limited to feeding it something very non-interacting like dark matter at this point. Think of a more normal scale black hole as a big pond or lake. It's very easy to throw a stone into one, and even if it skips, it's going to fall in after that. At some point, this turns into you trying to instead throw a rock into a fire hose while it's on. Hard, but possible. Maybe you need to fire a bullet from a gun to feed it instead, and beyond that we get to a point where we can't feed matter into one at all. You could conceivably pull over at an inhabited solar system with a giant power collector array that could force feed your black hole with an X-ray laser or maybe gamma rays, but now it's basically a battery for recharging, not a ship drive you could dump more matter into from a supply. Our 1.89 megaton black hole at 100 terawatts is quite an impressive ship, in that the black hole alone masses as much as 20 aircraft carriers, and the rest of the ship is presumably in that general size range. So this works great for space freighters and colony arc ships. Most often when folks talk about wanting to use Kugelblitz black holes this way though, they are thinking something more in the 0.189 megaton or 189 kiloton range, which produces 10 petawatts, and that is enough to comfortably light a continent. Though again, it being gamma rays means it's enough to easily sterilize a continent. This black hole lasts about 10 years and is half of a billionth of a nanometer across, and is allowing ships the size of a modern oil tanker to cross an interstellar void and at a high fraction of light speed to the nearest neighboring star. You want, of course, a smaller ship like the Millennium Falcon, on the order of tens of tons or maybe even a Kugelblitz black hole running your power armor. An 18.9 kiloton black hole produces a billion gigawatts of power for half a week, enough to light a handful of Earths, while a 1.89 kiloton black hole at 100 billion gigawatts lasts just 5 minutes. A 189 ton black hole at 10 trillion gigawatts would shine as brightly as a dimmer red dwarf star, but only for a third of a second. One as bright as our own sun and as massive as a large tractor at 18.9 tons would live only 300 microseconds. As a side note, I tend to be dubious if objects in this scale or much smaller but more energetic can really exist, though I am no cosmologist. Given that the upper end for the theoretical maximum vacuum energy is on an order of about 10 joules for 1 cubic femtometer, then by the time we get to our 189-ton black hole, this is trying to emit more than 1 billion trillion joules of energy from a region more than 1 billion times smaller than a femtometer or atomic nuclei. That would tend to imply a throughput or complete refresh rate of something just above a Planck time, roughly 10 to the negative 43 seconds, which is what we usually say is the hard limit of the minimum time any action can occur in. There's no half a Planck time. So I think at this point we can say that even if you somehow manage to get all around the creation and feeding issues, you have reached a hard limit on how small things are getting here, where we can definitely move into the Clark Tech range. No man-portable black hole generators unless you've got some method of anti-gravity or nullifying inertia, which might also allow some interesting approaches to energy creation. Some make a case there's also a hard limit at about 10 to the 16 kilograms or 10 million megatons, which has a power output of 3.56 watts and a lifetime of 1.47 billion trillion years. That's just over the threshold from soft X-rays to hard X-rays at 4145 eV or 0.3 nanometers wavelength, and thus is something we can comfortably work with. That value of 10 to 16 kilograms as a minimum is a number I encountered back when folks were trying to argue if the Large Hadron Collider was going to produce a black hole that would eat Earth. Though any black hole of that scale or smaller would take far longer to naturally eat this planet than it would live, the planet or the black hole. When you're trying to swallow an atom with a mouth smaller than one, and you need to eat untoward billions of them a second to even eat a planet over 1 trillion years, you have a constraint there that even Pac-Man couldn't overcome. If you cannot feed these things normal matter, then they need to be regarded as batteries, something civilizations do with a thin Dyson swarm of power collectors around their sun to store energy for the ultra-long term. They might be the ultimate commodity currency for civilizations too, the sorts of things you store in bank vaults at the center of artificial planets. For the purpose of artificial planets, when you just want mass, you probably still would rather use several smaller ones than one big one, which would mean placing them either in a magnetic field so they didn't merge, or putting them in something like a Kepler or Rosette configuration. Even the biggest of these is so tiny and carries so much inertia that they aren't going to be accidentally knocked off course by accidents, so storing them safely is a lot easier than antimatter, and they have the same energy density but can only be released at a certain rate. Though if you have truly good gamma-reflective mirrors, you could, in theory anyway, throttle a feedable Kugelblitz black hole by reflecting some of its energy back into it. Let's go over some other interesting sizes and applications, and thanks to my friend Bob Fowler for the chart he sent me that contained a lot of specific interesting black hole values I hadn't thought of. For spherical planets generating natural gravity equivalent to Earth's, their land area is proportional to their mass. Twice the land area of Earth, twice the mass. 1,000th the land area, 1,000th the mass. And similar, the amount of light they need to stay warm and comfortably lit scales proportional to land area or mass in this case. You need something like 1 watt of sunlight for every 25 million kilograms of planet mass. For a microplanet with something like Earth gravity and lighting supplied by that black hole, or by light generated from that power plant, your scale is around 10 to the 13 kilograms, a little over 1 trillionth of Earth's mass, or a 3.56 megawatt black hole, to potentially as high as 1 trillionth of an Earth mass at 10 megawatts. It would depend on how efficiently you generated power, turned it into light, and how close to Earth normal light and gravity you wanted. Their lifespan is on an order of 1 quadrillion years, so decently longer than the universe will be old when the last stars die. This would generate you about 1 trillionth the land area Earth has, or a millionth its radius, about 6 meters or 30 feet, just 500 square meters or 5,500 square feet, or 1/8 of an acre, in spherical format. This also means the gravity in your basement level is a lot higher than in your second story. Now, you wouldn't build a planet this small, but you might use hundreds of black holes in this mass range to make a microplanet dozens of times wider, or keep piling them in to get even bigger. But a pico-Earth mass black hole is probably your minimum mass artificial planet building block. You can also give artificial gravity to large flat regions of low gravity bodies for something like a spaceport by laying a bunch of these out in some 2D hexagonal arrangement, magnetically held in place. And that provides gravity and power, and again on a timeline of 1 quadrillion years. Also the high end of what you really want in terms of regular power generation for a civilization, because once you start getting to energy levels stronger than sunlight, you start getting heat issues. So while you might want some smaller and more powerful black holes for running something specific, like a space cannon or spaceship launcher, your own civilization on that moon or asteroid cannot really benefit from a higher energy density than this without melting. Same reason we wouldn't expect folks to bother with fusion reactors in the inner solar system around Mercury or Venus. The local sunlight is already as energy dense as what they can use on their ship or habitat, so any reactors like running your dryer in the summer with the air conditioner on instead of a clothesline, sometimes more practical but never really ideal under engineering. A rotating habitat would seem easier than this black hole hexagonal plating or grav plating, but may be higher maintenance, and more importantly, if your civilization is dumping all your sun's excess energy into Kugelblitz black holes to use trillions or quadrillions of years down the road, you do need to store those, and you might as well make use of their gravity in the meantime. I do not know if we will ever make Kugelblitz black holes a reality. I'm not sure our science is solid enough on black holes and quantum gravity to really speak with any certainty on their function or creation, but if we can make them, and given how easy doing a tinfoil-thick power collector Dyson swarm is, relatively speaking, I think Kugelblitz black hole creation is what you would do with all of a star's excess power generation until your population and demand there grew to reach that. In the end, it will all depend on how small a black hole you could make, and also how small a black hole you can feed, because the latter is always the control on using them for Hawking radiation spaceships. As we discussed, no matter what, black holes are likely to play a huge role in our future civilization, but if we can make subatomic Kugelblitz black holes function, they are likely become the go-to for both energy storage and power creation, and possibly the gold standard of the future when it comes to interstellar banking. Time will tell if it is possible or not, but the neat thing about even small black holes is they tend to be around for a long while, even compared to the stars themselves, and so with the civilizations that use them. While producing this episode, I got asked about making computers from black holes, and we'll be having one of our weekly shorts on the topic in a few days, but I've mentioned in some of our more existential episodes that you can build a computer out of all sorts of things, be it black holes or ants pushing grains of food around. If you can make a switch out of something, you can make a computer, and if you're looking for a fun example of that, there's Upper Story's award-winning game, Turing Tumble, that lets you build a computer that runs on marbles instead of electricity. It is a great game, and my kids instantly fell in love with it too. Turing Tumble, named for the great Alan Turing who helped us invent computers, is a fascinating and intuitive way to learn and hands-on experiment with the fundamentals of computing. It also comes with a wonderful graphic novel that gives you a story and presents you dozens of different challenges and switch diagrams to try, before modifying and experimenting on your own. Computers don't have to be a black box with mysterious workings inside, unless they are made of black holes, of course. Check out Turing Tumble at upperstory.com/TuringTumble to see why it won Parents' Choice Gold Award, Astra Best Toy for Kids Award, Toy of the Year finalist, and Dice Tower Seal of Excellence. Again, you can learn more about Turing Tumble and see it in action at upperstory.com/TuringTumble. Use the coupon code IsaacArthur for 10% off your total purchase. So that's it for today, and this weekend we'll close out the month with a look at multi-planetary empires on Sunday, March 31st, to explore what nations controlling several worlds might actually be like and how they would function. Then we'll start April off on the 4th with a discussion of space-based solar power and several other clean energy options from space that might be able to help us power not only our orbital infrastructure, but Earth itself, including options like Earth's own magnetic field. Then on the 7th, we'll return to the Fermi Paradox to ask if the reason why we don't see expanding alien civilizations is because they eat their own colonies in the Chronos scenarios. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show on Patreon. And if you'd like to donate or help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like Crystal Aliens at go.nebula.tv/IsaacArthur. As always, Thanks for watching, and have a great week.